Alright, well, over the past couple of weeks, we've been looking at these orbital simulations. We've got ones where they are perfectly circular, we've got other ones that are elliptical. Had a lot of decent initial discussion posts, but the reason why I made it a discussion was for you guys to actually add on to other students' responses instead of just making your own, answering the exact same thing that everybody else had just said. So, kind of a fail on that part, but I guess I could have pushed a little bit harder for you guys to just reply to other people that had originally posted. But let's go ahead and talk about these orbits. After reading all the posts, there's a lot of good stuff, but the wording is kind of weird. So if you're watching this video, hopefully you're looking for more clarity on that. If you're not watching this video, then hey, don't need to worry about it because you're not watching. So let's start off with those circular orbits. These circular orbits are perfectly circular, and that's the way that I made them. Looking at those circular orbits, you have only a force of gravity on the planet, and that's due to the interaction between the planet's mass and the sun. The sun is putting out a gravitational field, and we know that gravity, the force of gravity, or the field of gravity, gets weaker to the inverse square of the distance. And so as you get farther out, your gravitational field gets weaker, and a lot of people did say that, they did mention that. But there was a small issue that I noticed where you said, hey, you are farther out or you're closer in and your gravity is stronger or weaker and therefore you have to move and therefore the planet's moving faster, and there was no really good backup to that. So let's go ahead and talk about why the planets move faster the closer in for those circular orbits they are, and that's because that force of gravity is acting as a centripetal force. And so if that planet was not moving initially and it was affected by the force of gravity, it would get pulled straight in towards the sun. And so I'm going to try to run these videos as I'm talking, but if you look at one of the circular orbits, if that planet stopped moving, it would fall straight into the sun. Right now, it's just falling around the sun at the perfect velocity, such that as it falls, it gets turned. And so the gravitational force, is that centripetal force. Now, if that planet is farther away, yeah, the gravitational force is going to be weaker, so it's going to be weaker to the inverse square. So if I double that radius, it's going to drop that gravitational force and that field strength by not to a half, but to a fourth. All right, and so by dropping by increasing that distance, by dropping that force, the force that's causing the turning is now less, which means that you don't need to move as fast tangentially to make it in that nice circle. If you were moving at the same speed and you were farther out, then you would simply be moving too fast. And so as you fell around the star, if you're moving too fast, you would start to swing out and away from it, and you'd probably still get pulled back to it. You probably don't have enough kinetic energy to get away indefinitely. But you turn your orbit into more of an ellipse. So all orbits that exist are actually elliptical orbits. None of them are perfectly circular. Here I force circular orbits just so we can start talking about these in more simplified aspects. So as you are farther out, you get weaker force gravity, that is a weaker centripetal force, and that means that you don't have to move as fast to be turned by that force and still move in that circle. All right. There were others that said that, with the ones that had a doubled up mass of the sun, where they said, hey, let's if we doubled up the mass of the sun, yeah, the force is doubled, or actually the force is doubled because of double the mass of the sun, and they said therefore the planet is moving faster. But really, if we just instantly doubled the mass of the sun, that planet would not instantly be moving faster. It would still be moving at the same speed and just get pulled in towards the sun. Okay, so in order to exist in that same orbit, is a better way to say it, with the doubled mass of the sun, your planet would have to have that increased velocity. Now, it's not necessarily double the velocity, because there would be a square on your velocity term, and there would not be a square on your mass term. So while you doubled the mass, on the other side, you would have to have a square root of 2 times the velocity in order for your equation to work out, if you've ever worked the equations out. Okay, so be careful with that. Now, for your elliptical orbits, you have to talk about conservation of energy. Your conservation of energy really applies to all these, but with your elliptical orbits, they apply much more, because with your circulars, you really don't lose any gravitational potential if you're in that perfect circle, and so there's really no gain in kinetic energy. Now, your ellipticals, as you get farther away from the sun, that planet starts to lose that velocity, which means that it would be gaining that gravitational potential energy. And so if you were to draw the vectors at any point of your planet and your sun, you would start to see that at some point in your elliptical orbit, that force of gravity starts to pull back, not tangentially in towards, or actually not radially in towards the sun. And some component of that would be tangential, which means that it would either speed your planet up or it would slow your planet down. And I don't think anybody really talked about the components of gravity in your elliptical orbits. So take a look at those ellipses. Just realize that as that planet starts to swing out, swing out, swing out, swing out, there's a part of that gravitational gravity component that is pointing backwards, slowing that planet down. And as that planet starts to swing in, go faster, 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 part of the gravitational force, there's a component there that is actually in the direction of motion, which is going to accelerate your planet. Okay. Another big concern was that nobody really started talking about angular momentum until I kind of mentioned it, and I actually put it in the prompt. And so with the elliptical orbits, your angular momentum is conserved. It should be anyways. There's no outside forces here if that's the system. And just like energy. But if we talk about angular momentum, it's kind of like the ice skater trick, where if you are spinning around and you pull your arms in, you will start to move faster to conserve angular momentum. Here, with these planets, as they increase their distance from the sun, they are increasing their inertia. As in, if we look at mr squared for the point mass, like the Earth would be a point mass around the sun, as you increase r, that inertia would get bigger and bigger and bigger and bigger. And the angular momentum, having to stay the same, would have to respond by making its velocity, the angular velocity, smaller and smaller and smaller and smaller. And so, as that planet went out to conserve angular momentum, you would have to move slower. As that planet went in to conserve angular momentum, you'd have to move faster. And that was one thing that I really didn't see a whole lot of, or explain that well with a lot of discussion, or at least the initial posts that you guys were making. So, try to make two different universe sandbox simulations here. Hopefully, this can answer the question for a lot of you about how those different orbits work. There was a lot of kind of hearsay, kind of guessing. I know a lot of you just look stuff up and try to just copy paste it. But I really do want you all to understand how the gravitation works here, and especially with these elliptical orbits. And so once again, with the elliptical orbit, start your planet very, very close to the sun. It's moving, but it's moving too fast for that centripetal force of gravity to really turn it in that nice small circle, and so it's going to swing out. And when it's far, far, far away, it's still being affected by that centripetal force, but it's moving too slow, and so it really gets pulled back towards that planet. It gets turned a little bit too quickly. And so it falls back towards the planet. There's different ways you can look at these problems, either with forces, with energy, with momentum. But really, these are basic problems that you should understand how to work. Hopefully this explains a little bit more. So thanks for watching, and I will end it there.